Welcome. This is a run through of Level 3 Calculus 2025 NCEA examination 91577. Apply the algebra of complex numbers in solving problems. So let's just have a look and see what we can do. Question 1, part A, says when a polynomial 3x to the power 4 plus p x to the power 3 minus 4x plus 5 is divided by x minus 4, the remainder is 21, and the question wants us to find the value of p. We've got a nice theorem for this, and the theorem is called the remainder theorem. And the remainder theorem says that when x minus a is divided into a polynomial p of x, the remainder is the polynomial p evaluated at a. So what that means is we've got a equal to 2, and we just have to put x equal to a, which is equal to 2, into this polynomial, and we'll find the remainder. So we go 3 times 2 to the power of 4 plus p times 2 to the power of 3 minus 4 times 2 plus 5, and we're told that that remainder is 21, and this gives us an equation which will allow us to figure out what p is. 2 to the power of 4 is 16, 3 is 48, plus 8p minus 8 plus 5 equals 21. So we've got 8p here. 48 minus 8 is 40, plus 5 is 45, so this will be equal to 21 minus 45, which is negative 24. Divide through by 8, so we get p is negative 24 divided by 8, which is negative 3. So that's just a straightforward application of the remainder theorem. Question B. This wants me to do C, but let's get up here somewhere. Having trouble lining this up. Solve the equation x squared minus 6kx equals k squared for x. This is just a quadratic. The way you solve quadratic equations is we can use the quadratic formula. X is minus b plus or minus the square root b squared minus 4ac over 2a. And in order to do that, we need to identify a, b, and c. And they're easiest to identify when we put the quadratic into standard form. Standard form. And standard form just means write all of the terms on one side of the equation equal to 0. So we've got x squared minus 6kx already on the left-hand side. We just shift the k squared by subtracting from both sides, and we'll get this equal to 0. And this tells us that a is equal to 1. We don't write the 1 in usually. B is equal to negative 6k, and c is equal to negative k squared. Are the coefficients of the x squared, the x, and the constant term, respectively. So our x is going to be negative b, so just negate this, which will give us 6k, plus or minus the square root b squared. Square this, you get 36 k squared, minus 4. Our a was 1. Our c is negative k squared, and we need to divide all of that by 2a, which is 1. I'm going to run out of room, so let's work sideways. This is 6k. We're told to simplify your answer as far as possible, so we need to do a bit of work here. We've got 36k squared, and then minus times a minus is going to be plus 4k squared. 36 plus 4 is 40k squared, divided by 2. As I say, I'm running out of room, so I'll go sideways. We can rewrite 40 as 4 times 10, and we do that because we know the square root of 4, which is 2, and that's convenient because it's going to cancel with the bottom. So basically at this point we could take that and put it outside and then cancel. You've got to cancel a common factor, so you're effectively factorizing this, or you've got to divide the 2 into both terms on the top. And then this will be equal to, we've got 3k left, plus or minus the square root of 10, and we can square root k squared and get k. Normally you need to be a little bit careful when you're taking the square root of k squared, because it's easy to write that as k, but it's not actually k. You should put an absolute value around this. Let's just show you an example. The square root of -3 squared, which is the square root of 9, is equal to 3, and that's not equal to -3. So if we had k equal to -3, we don't get -3 over here. It doesn't matter on this particular question, but it will come up at other points. It doesn't matter here because we've got a plus or minus already in front, so not being careful about the sign of the square root of k squared isn't going to cause a problem because we're using both square roots at any rate, both the positive and the negative square roots. Question C, prove. Oh, all fun to prove. Again, this is just a quadratic. We've got an x squared term, we've got an x term over here, and a 3 over here. We want to know when it has no real roots. That's just telling us that the discriminant, which is b squared minus 4ac, the bit under the square root in the solution of a quadratic equation, that must be bigger than or equal to 0. If it's less than 0, there are no real roots. So anything bigger than or equal to 0 will give us real roots. So to identify A, B, and C, again, it's best to put this into standard form, which is put everything on one side. I'm going to multiply this out as I go. K's x all squared is the same as k squared x squared. I've got minus x over k over here. It's going to add it to put it on the other side. And I've got 3 here. I'm going to subtract that to get that on the other side equal to 0. Now we're in standard form. It's useful to simplify algebra often when you've got a fraction, as we've got here. So the fraction, we can avoid that by multiplying by k. Right through the equation, it will get rid of this. So k times the first term is going to be k cubed x squared. K times this term will just cancel the k in the denominator, and k times this term will just make us have 3k. And now we calculate the discriminant. B squared, our b is 1, so that's 1 squared is 1, minus 4, our a is k cubed, and our c is minus 3k. This is 1, minus times minus again will become plus, 4 3s are 12, k cubed times k to the power of 4. And we want to know whether this is bigger than or equal to 0. So we can easily tell that 1's bigger than 0, isn't it? And if we've got an even power, we always get a positive answer, except when you have 0, we're not allowed 0. So this term here will also be bigger than 0. And that means this whole thing is bigger than 0, not just bigger than or equal to, it's actually bigger than 0. And therefore, we will have not just real roots, but we will have precisely 2 real roots for all values of k that are not 0. We can't have 0 because we've got to divide by 0, but divide by k here, which would give us a problem. We wouldn't have we'd have an undefined equation. Part D. This is de Moivre's theorem. So we rewrite this equation as z cubed equal to minus 8m to the power of 27i. It's useful to draw an argon diagram. Our imaginary number is just purely imaginary. Our complex number is purely imaginary. So that means we've got a point down here somewhere. I'm having trouble changing colours twice. That is minus 8m to the power of 27i. We know it's down below the axis because 8's positive and m, we're told in the question, is a positive number. So m to the 27 will be positive. We've got negative that positive number, so we're down here multiplied by I. That tells us the argument of our complex number is all the way around here. It's 3 right angles, or 3 pi over 2. You could go the other way and get negative pi over 2. I'm going to use this one though. And de Moivre's theorem tells us that if we've got z to the power of n equal to r, a modulus, and then cis theta, an argument, then z is equal to, we take the nth root of the modulus, and we divide the argument by n, and we have to add multiples of 2 pi divided by n. And to get different multiples, you just put a k in here. I've not done that very well. So 2k pi. 2 pi is a whole circle. We divide the whole circle up into n parts, 3 parts in our case, and we add multiples of that to get various solutions. And we will get n distinct solutions. So let's apply that theorem to our question. We've got we want to write this in modulus argument form. The modulus is just the positive part of the number we have here, and the argument is 3 pi over 2. Now you could have added a 0 for a real part if you want, and this is you could have added a 0 up here for the real part. So applying de Moivre's theorem, the cube root of 8 is 2, the cube root of m to the power of 27, that's just multiplying 27 by a third, which will give us 9, and divide by 3 will cancel this 3 out, so it's pi over 2, and then plus 2k pi over 3. And we just put in various values of k, 0, 1, 2 will do, to give us distinct solutions. So we get z, maybe call it z1, is 2m to the power of 9 cis pi over 2. Put a 0 in here, you get 0, so that's done. z2, when k is 1, is 2m to the power of 9 cis pi over 2 plus k is 1, 2 pi over 3. That's 2m to the power of 9 cis Common denominator 6. This is 3 over 6. This is 4 over 6. 3 and 4, 7. 7 pi over 6. K equals 2. To get Z3, 2m to the 9 cis pi over 2 plus 2 2's are 4. 4 pi over 3. Again, the common denominator is 6. 3 pi over 6, 8 pi over 6, 3 and 8 is 11 pi over 6. And they are our three solutions. We're going to have a problem with this question. I think it's very problematic. Not because it's hard, but because the mathematics is a little bit sloppy in the way the question's posed. Sometimes when you have locus questions, you can get a long way with some geometry of the question, but the fallback position is always just to put z equal to x plus yi. Break z up into its real and imaginary parts and then work with the equation. So we're going to just replace the z that occurs twice in this equation by x plus iy and see where we get. X plus yi minus 5i minus x plus yi plus 5i equal to 4. And let's remember that when we take a modulus of a complex number, let's call our complex number a plus bi, what we get is we get the square root of the real part, a squared, and the imaginary part, b squared. So we square the real part, square the imaginary part, add them together, take the square root, and that's what this means. So in our equation, we've got a real part of x and an imaginary part of y minus 5. We've got a real part of x over here and an imaginary part of y plus 5. So what do we get? We're going to get x squared plus y minus 5 squared, take the square root, and we're going to get a square root x squared plus y plus 5 squared equal to 4. It's just writing out what the meaning of this equation is. What we want to get rid of these square roots. There's no square roots in the form that they want us to get up here. So we have to square this equation to get rid of the square roots. We can work with the equation we've got, but I think most people will find it easier if you shift one of these terms onto the other side first. So let's do that. Minus the square root of x squared plus y plus 5 all squared becomes plus when we shift it to the other side. And now if we square the equation, square the whole equation, it's easy on the left hand side, that's just getting rid of the square root. I'll take the liberty though of multiplying out this y minus 5 squared term. You should get yourself familiar with being able to do that. You square the first term, you square the last term, so these two terms are positive, and you get two lots of the mixed term. 2 5's, 10y, and it's got the minus sign that comes from here. Here we've got two terms, and we're going to have to be careful when we square it. So we square the 4, we get 16. We get two lots of the mixed term again, that's 8. 2 4's are 8 times the square of x squared plus y plus 5 all squared, and then plus we have to square this bit here, which is just getting rid of the square root sign again, and again I will multiply out the bracket. This time it's going to have a plus 10y in the middle, and that helps us because we notice we've got an x squared on this side, we've got an x squared on this side, we've got a y squared on this side, we've got a y squared on this side, we've got 25 on this side, and we've got 25 on this side, so a whole lot of cancellation occurs. which is going to make our life a little bit easier. Now if we put everything except this square root term over onto the left hand side, we can get rid of the square root by squaring yet again. So on here we've got minus 10y, the other side we've got plus 10y, so that becomes minus 10y. So altogether we're going to have minus 20y over on the left. We've got 16 here, that's going to become minus 16 on the left, and we've got 8 root x squared plus y plus 5 all squared. So that's simplified a lot. Before we square, we might notice that we've got a common factor of 4 in 20, 16 and 8. So we can divide by 4 and get 2, divide by 4 and get 4, divide by 4 and get 5. Usually making numbers smaller and not fractions will make our life a little bit easier. So now we square again. Squaring this side, we've got to square this term. We'll get 25y squared. We've got to get 2 lots of the mixed term. Minus times minus is plus. 5 times 4 is 20. 2 lots of that is 40. And we've got a y here. Square this, we get 16. That's going to be equal to square 2. We get 4. And then we get rid of the square root. And I'm multiplying out the y plus 5 bracket again. So we get this from squaring it. And now we want to collect together like terms. So we've got y squared here, which is going to be multiplied by 4. We've got y terms here. We've got just x squared terms here, and we've got plain numbers here. 25y squared and 4y squared. So that's going to be subtracting on the other side. Will leave us with 21y squared. 40y, 40y. Oh, that's nice. They cancel. 4x squared, that becomes minus 4x squared on the other side, and equal to 4 5s are 100, and minus 16. So 21y squared minus 4x squared equals 84. And we are in the form they require.